Okay, yeah, thanks for the invitation. So I'm going to give a science talk about recent work which got published last year. And the title of the presentation is Tropics-wide intra-seasonal oscillation. As you said, as introduced, it's a kind of a new type of or new phenomenon, which is related to the existing known intra-seasonal oscillations. So I want to start with a bit of background about tropical convection in general. I try to remove this floating controls. Okay, so here I want to show a bit of a schematic about the tropical atmosphere, which simply boils down to a small fraction of regions with very strong upward motion, updrafts, which is surrounded by weak subsiding motion over a vast region of the tropical environment. There's no major large-scale dynamics that exist in the tropical atmosphere. This is mainly because the impact rotation is very weak in the tropics, which distinguishes the tropical atmosphere with the extratropics. So that means the main balance which exists in the extratropical atmosphere, the geostrophic balance doesn't hold much. So the Coriolis force is very weak. In that case, the pressure gradient force as well as the temperature gradient can't really develop in the tropical atmosphere. This basically makes convection very important, leading to a quasi-equilibrium atmosphere. So any instability in the tropical atmosphere will quickly be removed by convection. So how does convection achieve this? We know that convection acts to warm the air around it, and this will create density differences. But however, because the impact rotation is very weak, this allows the gravity waves to travel over a very big region in the tropics. So therefore, the gravity waves are very efficient and very fast in homogenizing the density differences in the tropical atmosphere. And this ends up leading to a tropical horizontal temperature structure with a very weak temperature gradient in the horizontal direction. And vertically, the temperature in the tropical free troposphere is determined by the temperature of the deep convection. As we say, convection is very important. And because convection shoots up very quickly, it follows a process. It can basically conserve its energy, which it gained in the boundary layer. And so therefore, it follows a process which we call a moist adiabatic processes. So horizontally, it has a uniform temperature structure with a weak temperature gradient. And vertically, it follows, the tropical atmosphere follows a moist adiabatic lapse rate. So this leads to the initial picture that I said. There's a small fraction of region, very strong, with a very strong convection upward motion, surrounded by vast regions with very weak subsidence. So yeah, but if we average these motions over a month or even longer, what we see is a mean state of the tropical climate system, which we see the two important circulations. So there's the Hardy circulation, which occurs meridionally. It is a meridional overturning circulation with rising motion near the equator and subsiding motion in the subtropics at around 30 degrees in latitude. So this is the mean state, but depending on the seasons, the exact location of the Hardy circulation will move north and south. On the other hand, there's also the zonal overturning circulation, which is Walker circulation. In particular, we care about the Pacific Walker circulation, which has a rising motion in the Western Pacific and a subsiding motion in the Eastern Pacific. So also the Walker circulation, what we talk about here is the mean state. It will also move slightly depending on the ocean SST pattern, sea surface temperature pattern. In this schematic, it also shows a little bit of the monsoon circulation. But what I interpret is that the monsoon circulation is part of the circulations we talk about here. It's part of the Hardy circulation or the Walker circulation. Yeah, so that's for the mean state. And beyond the mean state, locally, there's local convection as well as very, very abundant equatorial waves. Here, this figure shows power spectra, space-time spectra of this brightness temperature. So the brightness temperature is the cloud temperature that we see from the space, cloud top temperature that we see from the space. So the power spectrum here, this plot shows, first, there's this very pronounced eastward propagating equatorial carbon wave, which occurs at a very fast frequency. There's also the westward propagating equatorial Rossby wave. In addition to the waves, and there's also this phenomenon, which we call the Madden-Julian oscillation. So I want to introduce a bit more in detail about the Madden-Julian oscillation, MJO. MJO is eastward moving disturbances of clouds, rainfall, winds, and pressure, which travels around the planet in the tropics and returns to its initial state in about 30 to 90 days, which we call intra-seasonal timescale. So specifically, the signal of the rainfall and clouds initially start from the Indian Ocean, as shown in the schematic, from week 1, and then slowly, and when we get to week 2 and 3, it moves to the American continent, including circulation. And by week 4 and 5, it moves further eastward to the Eastern Pacific. In addition to the signal of the rainfall, the wind and pressure signal actually travels further eastward. Here is an animation of the MJO movement, MJO activities. So the brown color shows this reduced OLR, outgoing long wave radiation, which signifies enhanced convection and precipitation. You can see it moves from here, the Indian Ocean, to the Pacific, which then further eastward. But the signal gets weaker once it moves, once it passes the Pacific Ocean. So that is the MJO. So here we basically talk about some of the fundamentals about the tropical atmosphere, from convection to the circulation, and then locally there's this waves and Madden-Julian oscillation. And now I want to come to the question that I'm asking in the beginning. So the question is, what processes can trigger tropical mean oscillations? So what I mean tropical mean oscillations is that this kind of signal, oscillation signal, is so strong and widespread. Even when you average the data over the whole tropical domain, you can still see the signal. We can think about the process we talked about earlier. There's these fast processes like the waves and MJO, and also slower processes like circulations. So it's probably a bit hard to just think about it, but the good thing is in climate science, we have a lot of data. So here, we're just going to do a simple preliminary analysis. We look at the daily time series of the top of atmosphere radiation from CNRS. So CNRS is a satellite observations of the radiation. So what's plotted here is a 10-year daily time series of the top of atmosphere net radiation averaged over the broader tropical domain, 30 degrees north to 30 degrees south. And as you can see very clearly, there's very, very regular oscillations, which occurs every year repeatedly. This is basically reflects the seasonal variations. Even though we average data over the whole tropical domain, the location of the Inter-Tropical Convergence Zone, which changes following the movement of the sun. And this also triggers the cloud response, therefore leading to oscillations of top of atmosphere radiation, which follows the seasonal cycle. And we can try to smooth out this seasonal cycle. And what we get here in the bottom figure is a much smoothed time series. Now we don't see the regular seasonal cycle, but what we see here is a much slower oscillation, which in this figure is mostly the internal variability. For example, here in 2009 is a strong La Nina year, which is followed by a strong El Nino year in 2010. Yeah, basically, based on this simple analysis in the tropical mean oscillations, we see the seasonal cycle. We also see the internal variability, such as El Nino Southern Oscillation, and so on. And as we can see, the process which we see here are mostly very slow processes. These are the processes which can effectively modify the circulations. So for example, ENSO, we know that it's able to, the changes in the SST patterns, sea surface temperature patterns can modify the Walker circulation as well as the Hartley circulation. This kind of, once the circulation is modified, it can very effectively lead to the tropical mean response, which can be reflected in the tropical mean signal. So these slow processes we know are very effective. But what about the fast processes, such as the Madden-Julian oscillation, MJO? So here we just look at the outgoing long wave radiation signal, which is filtered over the MJO frequency. Then we do a power spectra of this MJO data, MJO OR data. So we select the data over two different regions. One is over the warm pool region, which is a region which you always have active convection, which is, the figure is on the left, and the other one is the tropical mean. We average data over the whole tropics and look at the signal. First, we focus on the warm pool region, and you see so the MJO over the MJO frequency, there's very strong kind of power. But for the same kind of data set, if we average over the whole tropics, the signal is very weak. It's basically flat. So basically, at least from this analysis, it appears that the MJO filtered ORR doesn't really have a signal over the tropical mean. So why is that? If we look at the MJO pattern spatially, it leads to positive and negative anomalies in the ORR or in the precipitation. But if you average this signal, these are the different phases of the MJO from the early stage to the later stage. If you average these kind of variables spatially, this positive and negative pattern, negative signal will basically cancel out. So what we get is basically like very little signal if you look at the tropical mean. So therefore, the idea is that MJO, as well as the tropical waves, they can often induce very strong regional response locally. But if you look at the tropical mean scale, the signal is likely very weak. At least the direct effect of the MJO or the waves is very weak. So I want to summarize a little bit what we see here. What processes can trigger tropical mean signals? So we see the seasonal cycle, we see the internal variability. These are the very slow processes which can modify the circulation. But we also see for the fast processes like the waves and MJO, they don't seem to show a very pronounced imprint on the tropical mean. But then that basically leads to the question of this talk. Basically, do observations show evidence of tropical mean oscillations at intra-seasonal timescale, the fast timescales? We don't seem to see based on this simple analysis as I showed earlier. But if so, what are the key characteristics of these tropical mean oscillations? And how do these tropical mean oscillations relate to the existing known intra-seasonal oscillations? And to answer these questions, I'm going to analyze the reanalysis data from Error 5, which forms the main analysis here. But some of the key variables, such as the sea surface temperature, the atmospheric temperature at 500 hectopascal, and the top of atmosphere radiation, are also validated by some observational data, such as satellite data. Okay, so let's come to the result. First question, do observations generally show evidence of tropical mean oscillations at intra-seasonal timescale? So here, basically what I do here is to average the data over the whole tropics and then remove its seasonal cycle. And then I plotted the daily time series. Here I show three variables. SST as in the top panel, the atmospheric temperature at 500 hectopascal in the panel, and the top of atmospheric radiation in the bottom panel. As you can see, the time series, the daily time series of these variables are not really smooth, but rather showing very, very clear oscillation signal. And this exists in all three variables. To confirm the frequency of the oscillation, we do a power spectra of the tropical mean SST, which is this variable in the top. And what we see here is a very clear and pronounced oscillation power over inter-seasonal timescale at around 30 to 50 days. So which confirms there's like this inter-seasonal oscillation in the SST. This kind of power peak also exists in the other two variables, which I'm not going to show here. So this allows us to focus on the time scale of 30 to 60 days. So in the three figure on the right, we basically filter the data over the 30 to 60 day time scale. And what we get is a much more clear signal of these intra-seasonal oscillations. And if you look very closely into the phase relationships across these three variables, you will see they're closely related. When SST is in its positive phase of the oscillation, the atmospheric temperature is in its negative phase, while the top of atmosphere radiation is in its positive phase. So that means these variables are clearly related in terms of there's some process which behind it, causing them to covary. Another thing is that the oscillations, the oscillations that we see here exist in a lot of variables. It's not just limited to three variables. And because of its abundant existence, the widespread signal, we name this oscillation a tropics-wide inter-seasonal oscillation with the acronym TIFR. And in the next few slides, I'm going to try to understand the relationships across these three variables. As I said earlier, in order to have a very pronounced tropical mean oscillation signal, one important factor is that the circulation would oscillate. So here, we want to check whether circulation oscillates. So to define here we first define a tropical circulation index, which is based on the 500 hectopascal vertical velocity. We use the downward vertical velocity average over the tropics minus the upward vertical velocity. So what this index captures is the kind of total overall overturning circulation strength, which includes both the Hartley circulation and also the Walker circulation. Then we do the same time series and to see whether this circulation also oscillates. It looks like circulation TIFR also involves the tropical overturning circulation oscillation, as you can see in both the deseasonalized time series. It already shows the oscillation signal. And then we will try to look at the relationships of other variables with the circulation. So we try to understand the spatial patterns of the oscillation. What are the key characteristics of the tropical oscillation in space? So to do this, we're going to apply a lead lag regression analysis. We will regress the tropical circulation index, which is defined in the earlier slide, onto the spatial distributions of other variables. So for example, here, we look at 500 hectopascal temperature. So we regress the time series of tropical mean circulation index in the numerator onto this time series of the atmospheric temperature in space. This is three-dimensional in space and time. So this kind of regression analysis will give us a spatial map of the regression coefficient. Usually, a regression coefficient reflects the covariation between the two variables. So here, to ease the interpretation, we want to interpret in one-way direction. We interpret this as when circulation maximizes at day 0 and what happens to the temperature. So here, a positive regression coefficient basically indicates that the temperature in this region is in its warm phase of the oscillation, therefore has a warm anomaly. Whereas the negative coefficient means this variable at this time has a cold anomaly when circulation maximizes. So we repeated the lag regression analysis from within 24-day window, from 12 days before to 12 days after, where day 0 is a time where there's no time lag. And we assume this day the circulation maximizes. So first, let's look at the atmospheric temperature response. So 12 days before the circulation maximizes, what we see is that the atmosphere, the entire tropical atmosphere, is in its cold phase of the oscillation, which means having a cold anomaly. And then by about day -6, you see this positive signal, which appearing over the American continent. And then at around day 0, this positive signal expands to the whole Pacific. By day +6, this positive signal is basically everywhere in the tropical atmosphere. And day plus 12, we started to see negative signal, which is cooling signal appearing over the maritime continent, which signifying negative phase of the oscillation. And if you look at the patterns of the oscillation, it clearly shows convection gravity wave interaction. So initially the atmosphere is unstable, then you see the warm anomaly here in the maritime continent, which signifies enhanced convective activities in this region, first appearing over the warm pool region. And then a further warming of the tropical atmosphere basically reflects a gravity wave homogenization, where convection, enhanced convection leading to enhanced gravity wave activities. And this gravity wave propagates, communicate the warming signal to the rest of the tropics within about a week to 10 days. So it's a very clear convection gravity wave interaction. So what about the sea surface temperature? The sea surface temperature pattern is in here in the second panel, second column. It basically oscillates out of phase with atmospheric temperature. So initially, the sea surface temperature it's in its warm phase of the oscillation, and at about day 0, it transitions, and afterwards it changes to a negative phase of the oscillation. So the changes in the SSE is actually very closely related to the changes in circulation, which leading to increases in surface wind speed. So the right panel, the right column shows the surface wind speed response following the circulation. So as expected, surface wind speed basically follows the circulation. Before circulation amplifies this, circulation strengthens, surface wind speed is very weak. And then at around day 0, when circulation maximizes, surface wind speed also increases to its almost maximum. So this kind of increasing surface wind speed following the circulation strengthening basically triggers leading to the cooling of the sea surface temperature, because increased surface wind speed increases surface flux exchange, which cools the ocean surface, leading to the cooling of the SST. If we combine these three variables, we will see a very clear convection circulation coupling, which I will describe in these three phases. Initially, atmosphere is cold, whereas surface is warm, circulation is weak, convection is weak. So it's basically, this reflects a low stability atmosphere where you have a colder temperature in the atmosphere with warmer surface. And then this leading to this will lead to convection enhancement. So convection first enhances over the warm pool region, whereas in the same time, the circulation is still relatively weak. So convection first responds to the instability. So convection signal appears first. What's happening after is also at the same time you have the circulation response, which leading to increasing surface wind speed. This cools the SST. In time, convection enhances the gravity wave processes, which lead to the warming of the atmosphere. So the warming of the atmosphere is induced by convection-generated gravity waves, which happens very quickly, whereas the cooling of the SST is due to the enhanced circulation, which is leading to the overall surface cooling. So this is a very clear convection circulation coupling process. So far we have seen a signal which is mostly basically a signal that is not like, it's not stationary. It doesn't really see any kind of signal of the waves or the MGO. Then we look at the same regression analysis, but with the ORR, the outgoing long wave radiation. Again, we do a lead lag regression from 12 days before to 12 days after. So what you see here is basically the blue color indicates reduced ORR anomaly, which signifies enhanced convection. And as you can see, there's a very clear eastward moving signal of the ORR anomaly, which clearly signifies the patterns of the MGO. As we know, the MGO moves eastward. So this basically gives us a question, what is the role of the MGO here in this oscillation? We asked, this basically leads to the question 3, how do these tropical mean circulations relate to the existing known intra-seasonal oscillations? So we asked the question, is MJO essential for TWISO? So to separate the signal of the MJO, so here we divide the total TWISO cases into the ones which happening during the active MJO and the ones which happening during inactive MJO. So we define the MJO events based on the classical MJO definition. Here we use the RMM amplitude. So we have a very strict criteria here. If the smooth RMM amplitude is above 1 for around 20 days, around day 0 of the TWISO oscillation, we will define it as active MJO, whereas the inactive one is during this period, the RMM amplitude has to be less than 1. So then we look at the spatial patterns, the whole molar plot of the OIR anomaly over the active MJO case and the inactive MJO case. So here, this plot shows a longitude time diagram where the x-axis is longitude from the Indian Ocean to the Pacific, whereas the y-axis is time lag from initially early period minus 30-60 days to after 30-60 days. Day 0 is a time when temperature oscillation to its peak, atmospheric temperature oscillation to its peak during the TWISO. So during the active MJO scenario, we see a very clear eastward propagation, which clearly signifies the existence of the MJO. And where in the inactive phase, what we see here is more like a local convection oscillation. The eastward propagation is basically gone. But in the meantime, we see a little bit of a westward kind of propagation signal, which happening over the Western Central Pacific. And basically, we don't know what's happening over here, but we can basically kind of confirm this is not an active MJO case. Then we look at the TWISO oscillations, the temperature oscillations, temperature time series during these two scenarios. What we see here is in both cases, TWISO exists. So that means TWISO can exist without the occurrence of the MJO. But in the meantime, what we also see that MJO is able to enhance the oscillation amplitude of the TWISO. As you can see there, during the active MJO phase, the amplitude of the TWISO oscillation is a bit stronger. But we can basically conclude here, MJO is not essential for TWISO. This basically leads us with two hypotheses for what drives the TWISO oscillations. So one is related to the MJO. Here we describe the MJO-related mechanism in 3 phases. So first, we have this background convection and background circulation. We have the Halley circulation and the Walker circulation. And the MJO-related convection circulation is basically to the west of the background convection. So we know that MJO moves eastward. When the location of the MJO convection overlaps with the background convection in the maritime continent, this basically leads to enhanced convective activities, which also, in the meantime, there will be enhanced circulation. So enhanced convection leading to the warming of the atmosphere, whereas enhanced circulation leading to the cooling of the SST. But MJO will move further eastward. Once MJO moves away from the background convection, what we see is that the kind of convection and the circulation basically relaxes to its background state. So the idea is that when the active phase of the MJO is in the warm pool, it will lead to enhanced tropics-wide circulation response, and also which lead to also the other variables to oscillate. So that is the MJO-related mechanism. But we also know that MJO is not essential. So this basically leads us to a second hypothesis, which is related to the internal instability of the tropical climate system. This likely resembles the radiative convective instability that we see in the idealized simulations. So here I want to first describe a bit of the RCE concept in the idealized modeling. So the tropical atmosphere can be simplified as a radiative convective equilibrium process,
in such a kind of atmosphere, it is very simple. There's no rotation, no large-scale circulation. So the kind of essential balance framework here is a balance between radiative cooling of the atmosphere and convective heating. So in such a kind of simple system, there's three main important processes. So there's convection, there's surface fluxes, and there's radiation. So when the sun comes out, it heats the surface. This leads to increased surface fluxes. And increased surface fluxes can quickly trigger enhanced convection. And convection acts to warm the atmosphere, which we call convective heating. And in the meantime, radiation acts to cool the atmosphere, which is radiative cooling. So the balance is between convective heating and radiative cooling. But as you can see, the time scales of these three processes are very different. So convection occurs very fast. It takes about a few hours to a day, which responds to the instability. Whereas surface fluxes takes several days to buffer the exchange between the fluxes of the ocean and the atmosphere. Whereas radiation is the slowest component here. It takes about 20 days. So because of this kind of differences in the time scale, this will lead to transient energy imbalances. And we kind of hypothesized this could trigger the instability. And indeed, in idealized modeling of radiative convective equilibrium, people have already found there's this domain mean oscillations occurring at inter-seasonal timescale. So here on the top left shows a one-dimensional radiative convective equilibrium model. Already in 30 years ago, this paper by Hu and Randall, they found that precipitation seems to oscillate over a timescale of 30 days. Whereas last year, there's another paper which used a three-dimensional radiative convective equilibrium model. They look at also the kind of response at the domain mean radiation here. So here shows a TOA radiation for the short wave as in the red line and long wave in the blue line. So what you see here is first there's a very slow oscillation, which happens over around 300 days. So that's roughly an interannual timescale. If you look very closely into the fast oscillations, which is embedded, this is the intra-seasonal oscillation that we talk about here. There's also this very, very pronounced fast intra-seasonal oscillations in a three-dimensional radiative convective equilibrium model. So we see that there's already oscillations that appearing in idealized radiative convective equilibrium simulations with a very simple setup. So we hypothesize this could also be the driver of the kind of oscillations we see here in the observations. So the idea is very simple. The kind of balance of the energy in the atmosphere is basically a convective heating and radiative cooling. Convective heating mainly comes from the surface fluxes, so this kind of equilibrium is not a constant equilibrium, but there's transient imbalances. So when there's an energy surplus into the atmosphere, there's positive atmospheric energy perturbation. This will basically trigger enhanced circulation. Whereas if there's a negative atmospheric energy perturbation, so there's energy deficit in the atmosphere, this will lead to weakened circulation. So we can basically do a lead lag correlation between this atmospheric energy with the circulation we defined earlier. So this black line shows a lead lag correlation coefficient between this total energy with the circulation. What we see is that this kind of the peak correlation correlates at day 0. So that means when there's energy surplus into the atmosphere, basically there's enhanced circulation. Whereas when there's basically there's energy deficit, there will be weakened circulation. We can further decompose the signal into the correlations with surface fluxes and radiation. And what you see here is the timing of the peak correlation is basically determined by the surface fluxes, where as the radiation basically correlates with the time lag. So that means radiation supports the oscillation here, but doesn't determine the kind of total energy signal, which is determined by the surface fluxes. So TIFR can potentially be driven by the RC instability from the interactions between convection, radiation, surface fluxes, and large-scale circulation.
So again, we try to explain this mechanism in 4 phases here. So initially, the atmosphere is in its cold phase of the oscillation, whereas the surface is in its warm phase. The convection is very weak and circulation is very weak. And at this point, surface flux is also relatively weak because wind speed is very weak. But however, the kind of warm surface and a cold atmosphere will increase air-sea enthalpy differences. This will trigger increasing surface fluxes even when the surface wind speed is very weak. So the surface fluxes will change signal here before the changes in surface wind speed and circulation. So changes in surface fluxes will quickly lead to increases in convective activities. So convection will quickly respond to the changes in surface fluxes. And this happens at a time when circulation is still relatively weak. And then we move on to the phase 3. It shows that now the circulation also strengthens at phase 3. And this increased circulation leading to the increased surface wind speed, which acts to cool the SSE. And in the meantime, atmosphere gets warmer because of the convection increases the gravity wave homogenization. So now we are in a phase where the atmosphere is very warm, whereas the surface is very cold. So it's it's an atmosphere with low stability. So again, at this phase, surface fluxes will change sign first. So it changes sign because the surface is cold, atmosphere is warm. So you have reduced air-sea enthalpy differences, which will change the sign of the surface fluxes. So again, convection quickly responds to the changes in fluxes, which convection, the intensity of convection weakens a little bit. And this happens at the time when circulation is still relatively strong. And finally, this leads us to the original state where the circulation also becomes weaker, leading to a reduced surface wind speed. Therefore, the SSE increases and the atmospheric temperature cools because convection weakens. So this kind of processes can generate an oscillative cycle without the MJO here. So that's basically the second mechanism that we propose here, the RC instability mechanism. Well, in this paper, we didn't really say which one is right because we don't know based on the observation analysis. We can basically just propose these 2 hypotheses, and this needs to be verified using more data analysis or use models. So this basically leads us to the conclusion of this talk. So we asked 3 questions here, and we're going to answer them one by one. So first, do observations show evidence of tropical mean oscillations at intra-season timescale? So the answer is yes. We find very strong tropics-wide intra-seasonal oscillation among multiple variables in the tropics, and we name this oscillation as TIFR. So what are the key characteristics of the tropical mean oscillations? So this oscillation with a period of 30 to 60 days is evident across multiple variables and basically involves convection, radiation, surface flux, and circulation coupling. And finally, how do this tropical mean oscillation relate to the existing known intra-seasonal oscillation? So we found that MJO can amplify the oscillation amplitude of the TIFR, but it doesn't seem to be essential for TIFR to occur. And we hypothesize when MJO is inactive, TIFR is likely triggered by the instability of the tropical climate system, which resembles the instability of radiative convective equilibrium in RCE in idealized modeling. So that's basically a summary of the talk. I guess, as you can see, this is a very new results, which we have a lot of unknowns. And yeah, so I think there's a lot of questions. And if you're interested in this paper, please check out this paper. And also, I'm happy to discuss further about this topic. Yeah, thanks for your attention.
Thanks, Jiawei, and maybe we can take a few questions now.
Yep.
Hi, thanks for the nice talk, and the results are very interesting. So just wanted to know, like you talked about the MGO active phase, and that can amplify the this convective, all of these processes. So like I was wondering, so before the active phase of the MGO propagates, we normally have this suppressed phase, which also propagates with the downward motion and subsidence associated with it. Do you see, instead of amplification, a reduction of the oscillation strength with that?
Yeah,
If you see
I think
yeah.
I guess that's basically because what I show here is it's basically an anomaly with respect to the background. So I would say this kind of negative oscillation phase would be likely induced by the negative phase of the MGO oscillation in active MGO phase. So if you have subsidence over the maritime continent, you might leading to a weakening of the background circulation, which leading to basically the negative phase of oscillation we see. I think the schematic perhaps has some problems because the background state would be blue. The blue would be triggered by the negative phase of the MGO oscillation, I think.
Okay.
Yeah.
Okay, thank you.
I hope that answers the question. Yeah.
Yeah, thank you.
Hello. Yeah, this is a nice talk. Regarding the first question that you have answered about the observations, though the oscillations are generated in the atmosphere and they are enhanced by the ocean, you are using of ERA 5 reanalysis as observation. How do you take that coupled processes? Because the ERA 5 is a prescribed FCT. So how do you? How do you?
I think. Yeah. Okay. I guess I think you were asking questions about whether ERA 5 is basically based on a atmospheric model. How do you interpret this as, because this is an ocean atmosphere coupled process? Is that the question?
Yep.
I guess ERA 5 is not just a model. It's basically homogenized a lot of observations. I want to go back to the initial time series here. Basically, ERA 5 is the one we decided to use in later because it has a lot of data. But the original signal is basically verified with another source of data, either observations or reanalysis. For example, the SST here is basically verified with OISST. If you look at the filtered signal, it's basically the same. And that also applies to the other source of data, the ERA 5 and a series for radiation, the ERA 5 and a mirror for temperature. So the signal of the ERA 5 is basically agrees with another source of data, which made us think basically ERA 5 is able to capture the signal of the observations. And the ERA 5 itself is homogenized with a lot of observational data. So I guess my conclusion is the signal is robust across multiple data sets.
Thank you so much for that talk. Some great results to take away. My question is, does ENSO have an impact on the power of the intra-seasonal oscillation that you see? And a follow-up is if the NJO has different impacts in how it strengthens the oscillation itself. Because SST sort of set the, that's my question.
Yeah, thanks for the question. I think this is, as I said, this is the early study. We don't really know exactly about how this process affected. But I think a preliminary analysis, which I'm currently preparing, is that if I composite the oscillation into different ENSO phases, we don't see a difference in the signal, which seems to suggest ENSO doesn't seem to play a big role in the oscillations of the TWISO here. We don't see a difference in amplitude when we composite the ENSO phases. And the second one is about MGO. As I said, MGO seems to be amplifying the oscillating signal. I think this likely is related to MGO really induces a very strong perturbation into the convective activities in the warm pool. So therefore, it's able to cause a bigger departure from the background state, bigger perturbation, compared with the case when MGO is not active, I think. But I think exactly how it affects the oscillations, we still need to verify it.
Yeah. Hi. So You've talked about the MJO and the gravity waves. So what about the role of low frequency equatorial Rossby waves, which do have a frequency domain that might fall in this, what do you see? Because literatures in the past have shown radiative convective equilibrium associated with low frequency equatorial Rossby waves. So what do you think, like the role of?
Yeah, okay. I think in analysis, I didn't really see the Rossby wave coming out from this analysis. But again, this is just like an observation analysis. It's really hard to get a lot of to do a lot of analysis. But at least from the preliminary analysis, we don't really see the influence of that the Rossby wave signal. What was the second? I'm not sure if I answered your questions, but yeah, there's a lot of things to do. I probably I need to look into the MGO, the Rossby wave influence a bit more into the detail.
Thank you.
Okay.
Hello. Hello. Why the temperature at exactly at 500 HPA carries so much importance, not any other level temperature?
Oh no, it's basically having a signal in all troposphere. But I think usually we chose one characteristic pressure levels and to show the free troposphere. I guess I happen to have the data of 500 hectopascal, but I think you will also see the signal over maybe 300 hectopascal or maybe over 600 hectopascal.
It is due to the
because basically the free tropospheric temperature. Yeah.
And it is due to the 0 degree isotherm that is present in this region.
No, it's basically the free tropospheric temperature is determined by convection, which is basically spatially uniform. As long as you look at the temperature in a free troposphere, you should be able to see the signal. It could be in below the isotherms, it could be above the isotherms, because this is a temperature determined by the deep convection through the gravity waves. So it doesn't matter which height you look at.
Thank you.
Yeah, thanks, Jiawei, for a very nice talk. I think I appreciated your work much better now than when I read your paper. Very nice talk. So my question is, actually, you are essentially putting the whole literature upside down, I feel. You're saying maybe spatial gradients do not matter, but instead just the asynchrony of how evaporation processes happen and how radiation is a slow. So asynchrony between these processes essentially give you the intra-seasonal time scale. Is that interpretation correct?
I think about the time scale, it's a good question. I'm still asking myself why it happens over this time scale. I think based on the initial hypothesis, at least in idealized models, you also see similar time scale. So that basically led us to the hypothesis that basically just these interactions can give you this time scale. But we don't really have a good idea, like what determines, I don't know. It's just like a hypothesis. But whether this is robust or not, we don't really know about the timescale thing. I don't know how to answer this question. I've been thinking about it. Yeah. I think first how do we approach this question? Perhaps we should go back to the idealized models and try to play with it and see whether timescale changes, and then we can come back to the observations and to test these ideas. Yeah. I can't answer your question, sorry.
Yeah, thanks, Jiawei. Yeah.
I think we have one online question, and then we will have one more, which will be the last. Can the online participant type the question or unmute and ask?
Hello.
Yeah, we can hear you.
Hello.
Sir, my one question, I will ask one question, sir. Can enhanced convection, circulation, coupling, and RC instability under climate change contribute the increasing persistence of wet extreme and clustered event rainfall?
So you're saying, can the interactions of this oscillation change on the climate change, which enhances the occurrences of the extremes? I'm sorry, is that the question?
Sir, actually, I asking sir कि the persistence of wet extreme and clustered rainfall events will be enhanced due to convection circulation coupling of RC instability under climate change.
I guess this is a very hard question because we haven't looked into climate change thing yet. So this is still like a very, very early results, which we look at the current state. And we don't really know whether this is this kind of oscillation, how does this oscillation change in a warmer climate. But I think just by itself, this oscillation would definitely affect the extremes because it's basically oscillation itself is a departure from the mean state. So this kind of oscillation can basically interact with other oscillations, leading to greater extremes in different places. So I think at least for the current climate, we can definitely expect this oscillation would affect the extremes. Whereas how it changes with warming, I don't know. Yeah.
Okay, thank you, sir.
Thank you.
Hi. Hi, thanks for the nice talk. I have just one naive question. Since in your talk, you have talked about tropical factors which may contribute to the amplification of these tropic-wide intra-seasonal oscillations. I just wanted to know if there is any impact from the extratropical wave intrusions or any sort of remote forcing from the extratropics. If you can just comment on that.
I think well, the answer is also I don't know. But I think as our analysis showed, there's oscillations in the tropical energy which would definitely interact with the extratropics. So whether it's extratropics drives the tropical oscillation or whether it's tropical oscillation, tropical signal affects the extratropics, we still need to look into it. But I'm sure this oscillation will also interact with the extratropical dynamics. It could be the extratropics modulating the tropics. We don't know. Yeah.
All right. Thanks.
Thank you.
Thanks, Jiawei. That was a very nice talk. And thanks for waking up early and giving this talk at our time in Europe. So maybe let's just have another round of applause for Jiawei.
Yeah, thank you.
Yeah. And now we can move on to the next talk. And